a little bit of time for people to sort of log in and for the various different YouTubes. And I'm streaming to YouTube and to Twitch as well. So Twitch being the gaming platform. You done any Twitch stuff?
I sometimes watch chess. Sometimes
Oh,
watch chess.
oh, really?
Yeah,
So are you watching chess or are you playing chess
I
with people?
I both. Yeah, but I'm not
Oh,
so good.
no, neither am I. My son beat me at chess probably at about age 12, and then I was so grumpy about it. I was like, "Oh, forget it." You know. Well, I'm distracted or something. Yeah. So you know what this is like. It's
Yeah, a bit. Yeah.
but it's fun. I just really like the process of having other people in the conversation because even though I'm terrible about focusing on chat while we're talking, because I feel a bit like it always feels a bit like a teenager with a cell phone. You know, you're distracted the whole time. So I try to have
Yeah.
a conversation with you. Agne is fantastic and sends us the questions and stuff. And we've got Cal. Cal is one of my moderators who's just fantastic. I call her the hammer because if anyone gets out of control, Cal comes in and just thumps them. Oh, good. Okay, we got people coming in now. Great. So, hello, Mittens. Hello, Paranoid Badger. Great names. And I shall get us started. Let me just double check on the Twitch side of stuff. There we go. Oh, we are live. Very good. Very good. Look at that. How is sound and everything for everybody? Danish Duckling, the Rion Pyrus, Sylvic99. Hello, hello. All good? Everyone likes the sound? We're good with this? Let us know right away if there's any problems or anything. Of course, Agni will also do that as well. So, ladies and gentlemen, the interwebs. It is I, Hewlett, David Hewlett, and I am very, very excited because today we are talking to Xavier Dupac. I don't know if I'm butchering that in my horrible American accent, but
Maybe.
welcome. Yeah, thank you so much for doing this. Maybe you could let
Thank
people
you.
know what you do. What is
Yeah.
your role?
So thanks for having me, David. It's a real pleasure. So yeah, I work at the European Space Agency, especially on what we call the Euclid spacecraft. So
Yeah.
this is a mission that has to do with observing a lot of galaxies. It's a cosmology mission, so it's what we want to see is also the dark matter, the dark
Yeah.
energy, dark universe stuff that
Yeah.
we don't know much about. And with this mission, we hope we're going to have good data. We already have good data,
Oh
by the
my
way.
God.
So for the people who know about redshifts, typically something beyond the redshift 0.5 is everything we want to see. So it's looking at the history of the universe,
How does
really
the
how the
redshift work? It's basically that's how you're gauging how old things are or how far away they are. Or...
Right, exactly. So both. So what we see is that most of the galaxies around us are receding from us.
Hmm.
So we know that because we see that they're redshifted. So it's the Doppler effect.
Right.
So it's the same effect as when you hear the sound of an ambulance coming towards you. You hear it's slightly higher, and then it goes away, and you hear it lower than what it is. Right.
It sort
So
of
this is
squashes as it speeds
exactly,
up, doesn't it?
yes.
Yeah.
So
Yeah.
that's the Doppler effect. So it works the same with sound and with light. So in the case of galaxies, we're observing the light. So especially we're observing the lines of some of the atoms present in those galaxies. And that was actually a very funny discovery that was made in the beginning of the 20th century by people like Hubble and all these people. So
Yeah.
they
Yeah.
started looking at all these galaxies because before that we didn't know there were galaxies. People thought that the whole world, the whole universe was what we know now to be
Right.
our own galaxy, okay,
Right.
the Milky Way. So now with Hubble, they saw all these external galaxies, and after a while they realized that after a certain distance, that most of those galaxies, or all of them, they were in fact all redshifted. Which was weird because you would expect that some are blue shifted, some are red shifted if it's a static universe and things are moving
Coming and
slightly
going,
direction
and
or let's say randomly like let's say the particles of molecules of air in a room. Okay, you will have molecules coming towards you, you will have molecules coming away from you. But in the case of galaxies, we see all these galaxies going away. So that was really strange results, and it was confirmed so on. So that's how basically
When did we
know.
find that out? When was that discovery made? I feel like it
Was
was
in
fairly
the
recent.
the 1920s, 30s.
Yeah. Yeah. Okay. Right. Yeah.
It's quite a long time ago already. But then it was refined, and then it was understood that this was because the space itself was expanding.
Right.
So that's what we call the expansion of the universe. So this is what we're interested in with Euclid. We are going to look at all those galaxies, as many galaxies as possible. So we aim to have something like a couple of billion galaxies in our data sets. So it's quite a lot.
Yeah, your
But
data set.
also
You're the
just
one who's got to
for
handle all this
for
data, right? You're the one who's got to deal with it all.
Right, so there are many people, of course, but it's a challenge just to get the data on ground, also to do the data processing and to do all the data analysis of all this data. It's quite a challenge. Yeah.
Okay, I'm dying to talk to you about the actual Euclid program, but let's go back for a second. Like, how did you get here? Because you've been working on some fun stuff before this as well.
Yeah, exactly. So before Euclid, I was working on the Planck mission, that's another ESA mission. And that one was on the cosmic background. So it's even looking farther away in the universe. It's really looking at the first light.
Right.
So the cosmic background is really the first light that you could see from the early universe. So it's only 380,000 years after the Big Bang. So it's quite early.
How do you know that? Like, how on earth do you figure that out?
So basically, it's a bit you also measure the redshift of the cosmic background, because you know the process.
Yeah.
So essentially, you understand what happens is that during the very early universe, the universe was not transparent; it was like a plasma. So it was like the surface of the sun, let's say. So it was like a plasma. So the temperature, you understand the physics, so you understand more or less the temperature of this plasma, and you understand what happens when the atoms start to form. At some point, this plasma of just nuclei and electrons, well, it's with the expansion of the universe, it started cooling, and it became gradually less dense. So when it becomes not so dense, then and not so hot, then the atoms can form. And that's at this point that that when atoms form, they emit some light.
Right.
So this is at some point. So at this point in the history of the universe, there is all this light that is emitted, and that is what we see today as the cosmic background.
Right.
So at the time, it was in the visible light. It was actually in orange. So
really?
You could have been there with your human eyes. You would see the universe filled with orange light.
Wow. And then that's just redshifted as it's gone along.
Exactly.
So now it's what, in the infrared or whatever, or
so then it went to the red and then into the infrared, and nowadays it's even beyond that. It's in the microwaves now.
Oh, wow! Okay.
The temperature today of the cosmic background is 2.7 Kelvin. Yeah. So it's really, really cold now.
Right. It's a little
chilly.
chilly.
So to observe that, you need specific detectors. You need this special cryogenic spacecraft to cool down all the detectors of very, very low temperatures, so that you can actually measure these little fluctuations over this background.
How do you keep the satellite cool? It's got to be fairly passive, doesn't it? I mean, you're not powering that, are you?
So in the case of Planck, because we wanted to see the cosmic background, it had to be actively cooled.
Oh, really?
So actually, yeah. So actually, one of the instruments, there were two instruments, but the one that's most cooled is the one we call the high frequency instrument, and that one was cooled down to 0.1 K.
Oh, wow!
Can you imagine?
Yeah.
So it's quite cold. It's really remarkable because this kind of temperature doesn't exist anywhere in the universe.
I was going to say that's like not even that's human creativity cold.
Yeah, exactly. So, but this is necessary to measure this. But in the case of Euclid, so my current mission, we don't need that. So it's just passively cooled.
Oh, great!
Because we observe in the visible light and in the near infrared. So in that case, you don't need to have these special detectors that are cooled with cryogeny. So in our case, it's just let's say normal stuff like CCDs, these kind of things. And spectrometer for the infrared also.
And is Planck? I'm assuming Planck's still going to some extent. Is that or
no? Planck it worked 4 years between 2009 and 2013.
Oh, wow!
And then it stopped working because in the case of this all this cryogenic stuff, it's difficult to make it for a longer time.
Yeah, I was going to imagine. I mean, especially if it's active cooled, you got to have everything.
Yeah,
Everything
you
going.
need all the energy there and all the.
And is that the
the
lifetime for those? Like, is that what was sort of planned for that kind of thing, or was that?
Yeah, that was actually the plan was only 2 years.
Oh, really?
Then
Okay.
it was extended.
Right.
But
Okay.
yeah, for those ones, but for Euclid it's more. For Euclid now it's 6 years mission.
Wow.
But again, it's not cold, so it's easier to make it longer.
I mean, it's still quite a process, I imagine, because even just, I imagine, the side, there's going to be hotter sides and colder sides, and trying to keep everything in that, as well, especially with the Planck stuff, I guess, is trying to keep that stuff at the right temperatures, even just within these.
Yeah, so this is the whole design of the spacecraft is done such that you cannot protect the cavity where the instruments are. So this cavity you have to keep away all the stray light and the temperature fluctuations as much as you can so that it's stable. And so typically you don't you try to keep your spacecrafts with the same face towards the sun
all the
somehow.
time.
So you
Generally, that's
so you can orientate it a little bit. You can you move it a bit, but you don't want to go very quickly or
Right.
or with very wide angles away from that. Otherwise, indeed, as you point out, it would make too much difference in temperature, and
Right.
so it would not be good for the measurements. So we need stability and really quiet stuff.
And where was Planck positioned, and where is Euclid positioned?
So both went to the what we call the L2 point, the Lagrange 2 point of the CERN moon systems. Sorry, Earth moon system. So this is a kind of not so stable, let's say, semi-stable point in the let's say the three-body problem, right? So you have the sun, you have the Earth, and you have the moon, and then you have so you have these stable points that are in different positions in the Sun-Earth axis. And in the case of the Earth Moon, you have the same kind of thing. So you have one point that is called the Lagrange 2, the second Lagrangian point that is away from the Moon. But let's say it's always in the case of Planck and Euclid, it stays around this Lagrange 2 point. It's always in the same axis. Let's say it's in the same direction as the sun and the Earth. You always have the Earth and the sun on the same side.
Okay, all right.
This is good because you have all these strong sources of light on the same side. So you don't want to observe that way.
All right, because you wouldn't see anything anyways, because it's just too
bright.
Yeah.
Blinding you.
Yeah.
So you don't want these sources to blind you. So by keeping the sun and the Earth and the moon on the same side, you allow yourself to observe away from them.
And I guess that works too, right? Because you've got the solar panels on one side, and they can shade it as well, right? I guess is that.
Right, exactly. So the solar panel on one side, so always facing the sun with you have an angle that you can move a little bit, and then on the other side you have the telescope.
Yeah.
So in the case of Euclid, you have your telescope is like back to back with the solar panels. You have the solar panels like this. You have your telescope like this on that side. So we have the sun that way.
Right.
And we observe with the telescope looking up, and you can then move like this freely. You can observe
interesting.
That's a circle. Yeah.
Oh, that's
and then you
I didn't realize that. Okay.
You can move a little bit like this. So and also a little bit like this, but not so much because as I said, you always want the sun that way.
Right. But it's quite a wide field of view, so you're getting a lot. And you can, I mean, the quality of the images is extraordinary, and the detail of them is amazing. Are you taking multiple? Are you taking multiple images to get that, or is that sensor capable of getting that kind of detail just in a pass?
So for one area of the sky, we take 4 exposures. And we do what we call we dither, as we said, we dither a little bit between these 4 exposures.
Right.
And that's because they are in the CCDs. There are let's say there are holes in between CCDs.
Right.
So if you cover these holes, you have to do these 4 different exposures. So we do something like this: tack, 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 tack.
Right.
And that way we cover the whole area properly. Okay. So it's 4 exposures. But even just with one exposure, you can see also a lot of details, a lot of galaxies.
Yeah.
But with these four, you stack them and you get a better view. Let's say.
And it's CCD, but is it? And it's also you're also picking up microwave. You're also picking up infrared. What else? Is it just the? Is it just? It's not just images, right? It's not just visible images, right?
So for you with Euclid, we have the visible image, which is very good resolution.
Yeah. Yeah.
But is a monochromatic. So it's just a wide view. There is no colors, just one, let's say black and white if you want.
Oh, really? Okay.
Yeah. And then we have three bands in this near infrared.
Right. Okay.
So yeah. And then we have also spectrometers. So in order to see the lines in the galaxies.
Right.
Also in the near, two of them.
And those get put together into those glorious images that we see you post.
Yeah, so you've seen these images that were published.
Yeah.
They make use of the four bands, so the visible band and the three infrared bands.
Right.
So you have like four wavelengths. So you think that let's say for TV, typically for the computer screen, you have three or four, but it's like RGB, right? Red, green, and blue.
Yeah, yeah.
So for us, it's a bit similar. We use these four bands to make an artificial color image. But that is very close to what you would see with your eyes if you could have this sensitivity of your eyes in the visible with the three wavelengths you have on your eyes. You know that you have the red, the green, and the blue, the different detectors in your eyes. So that's what we try to mimic when we make an image for humans to see. So,
that's
but
brilliant.
in our case, we don't have RGB, but we have visible. We have the three infrared, so we can mimic that. Let's say.
Oh, that's fascinating. I hadn't even thought of that. I mean, I guess that makes sense. So you're just basically swapping them out. You're not getting all three colors, so you get three different. But you still get three different looks at
typically, if you had only the three infrared, typically what people do when they do infrared astronomy and they want to make a nice image, they assign the red to the longest wavelength in the infrared that they have, and then the middle one the green, and then the highest frequency the shorter wavelength the blue, and like that you make this image.
Well, okay, so we've got these images, and the whole point of this was fascinating because I was watching a bunch of ESA's videos, which are just amazing, by the way. If anyone hasn't checked out ESA's even just their YouTube channel, but their website is amazing. There's so much information there. They were examining these images coming from Euclid, and but a lot of them, most of them were talking about the things we could see, and I kept going, yeah, but it's about the dark matter. What about the dark matter? But we need those things we can see in order to figure out this dark matter. Actually, before we do this, what is dark matter? What is the deal with this?
Okay, so dark matter, essentially, we don't know what it is.
Well, okay. Well, thanks very much. Bye.
I mean, we know only a few things.
Yeah.
We know that it's not interacting at all with light.
Right.
So this is why we don't see it at all. It's actually the wording dark matter is not so good. I mean, we should call it transparent matter because this is what it is. Really.
Okay.
It's just transparent. You can have a big cloud of dark matter in front of you. You will not see anything. You cross it. No, you will not feel anything or anything like that. And only your gravity will be felt. So that's how we know that dark matter exists. Is that because we see its effect on other things.
So it has a gravitational effect on things.
Gravitational effect only. So there is no electromagnetic light, no electromagnetic.
It's not emitting anything. There's nothing for you to photograph.
There's no emission of anything. It's only through its gravitational effects that you know that it's there.
So this is where this lensing thing comes in. Is that right? That's where you're using these big objects to try to figure out how they're being warped by space, by dark matter.
Yeah. So that's something that Einstein figured out. That with
Einstein again. It's always Einstein.
With general relativity, that this effect can happen. That you have what is called a gravitational lensing. So it works a bit the same way as a normal optical lens, only that in that case it's gravity, it's mass that is the lens. So you can have in the background you have a distant galaxy that you can see, you wouldn't be able to see because it's too distant.
Right.
But you have in front of you, you have this big clump of dark matter that is acting as the lens. So this light from the galaxy is lensed and is deformed. So you see something like an arc around this big blob of mass that you can guess that it's there, but you don't see. But you see.
I always think of
it.
Interstellar. Interstellar always had those wonderful black hole images where you could see the lensing happening. It's a great visual of it.
See exactly. You see the lights curved around the black hole. And so it's a bit similar. So except it's not a black hole, but it's a big mass of dark matter, and it could be the cluster of galaxies. I mean, it could be many things. So in the cluster of galaxies, you have galaxies, but you have also dark matter. So that most of the mass is in fact in the form of dark matter.
And so when these galaxies you seem to be looking at the clusters a lot. What's the advantage of looking at the clusters? Is it just because there's more things to look at, or what?
Well, I mean, it depends what kind of lensing you're interested in. If you look at a big cluster, what you will maybe see is what we call the strong lensing. So you will have these nice images, these arcs.
Right. Okay.
We're going to see also on Euclid is what we call weak lensing, and this is something. It's the same thing, but it's for all the galaxies. Let's say that in fact all the galaxies are lensed a little bit because there is always mass in the line of sight.
Right.
So even though you don't see the effects with your own eyes, you have to analyze it statistically to be able to see the shear of all these galaxies behind this mass. But it's there, and it's possible to analyze that, and that's one of the probes that we want to use for cosmology for Euclid. That's one of the two main probes that we have. It's called weak lensing. It's exactly that. It's measuring the shear that is due to this mass along the line of sight. When you see a galaxy, then you measure the shape of this galaxy, and you have models that tell you that this type of galaxy could be this shape or that shape. So individually, you don't know if this galaxy really is. You cannot really conclude individually for one galaxy what the shear is, but statistically over many galaxies, you can do it. And so what it gives you is a map of the dark matter in the universe.
So mathematically, basically, you're saying a galaxy should look like this, but we're seeing it like this, which means this dark matter is changing its shape in that way. Wow.
Exactly.
So the more data, the better then, because you're going to get more and more accurate the more you've got to compare it to.
Yeah, you need a lot of data, and you need to be very careful with all the systematics, with all the noise. It's quite complicated, but yeah, and the more data you have, the more sky you have, the better.
So now pardon my ignorance here. Dark matter, dark energy. Difference? Yeah. There's a difference there?
Yeah, they are completely different things.
Oh, they are? Okay, all right.
Yeah, so dark energy is something, let's say, even more mysterious than dark matter. So in the case of dark energy, it's really something that we invoke because we see that there is an acceleration of the expansion of the universe.
Right.
So this is something that was discovered in the 90s with Hubble data, and then it was confirmed with other data and so on.
And that kind of threw us off a bit.
Yeah, because I mean, essentially, if you only have, let's say, the initial kick of the Big Bang, it gives you an expansion, but then gravity starts to pull things together again.
Right. So we should be
gravity is only attractive. So gravity doesn't pull things apart. Gravity only tries to attract them. So that works also for the whole universe. So in this respect, the whole universe works as a physical object.
Right.
If you apply the laws of gravity, and I mean, it doesn't matter if you take Einstein relativity or just normal Newtonian law. The basic law is the same. It's attractive.
Right.
It goes with the square of the distance, and it's so what you would expect if there's only these forces at play, that the right after the Big Bang, then you have, well, after maybe the inflation or things like that, but after all this is finished, you would have deceleration
Right.
of the expansion. You will continue to expand for a while, but decelerating.
Right.
And
Which
then,
seems intuitive. That seems to make sense. Like that's what we experience, right? I mean,
and then depending on whether we are above the critical density of the universe or below, then you have different scenarios. In one scenario, you have what we call the big crunch. At some point, it just stop expanding, and then it starts to collapse again. But if we are below the critical density, then it wouldn't happen like that. It would continue to expand, but always decelerating. They're never accelerating. But what we are seeing is something different. We're seeing that at some point in the history of the universe, so roughly halfway from when we are now, it started accelerating. So this is kind of mysterious, and for that you need to invoke either what Einstein called the cosmological constant, so
right.
the lambda, so the famous lambda called dark matter models. I think that's our main model now. And we need this lambda because this is this mysterious force that makes that things start pull things together instead of attracting them. So it's something.
But that's just a placeholder, basically, right? That's isn't it?
Yeah.
It's basically just going like, figure it out later.
Yeah, exactly. And the equation is what, as you say, it was something like, okay, I just add this constant because I need it. Actually, Einstein first put it there not for this reason that I described, but because he wanted to have a static universe. So he added that at that point, and then the observations came in of the Hubble flow and so on. So Einstein said, "Well, I was wrong," but then it turned out that he was right anyway because we need this cosmological constant for the other reason, that is to be able to explain to not explain, but to have at least the equation compatible with the acceleration of the space, of the expansion of space.
I mean, it's so funny. I mean, I know this is no mystery to people, but it still amazes me how much there is to learn from this. You know, that there's just what I think the number is something crazy, like it's like 95% of the universe is dark matter, and 5% is what we're able to see.
So 95% is in form of dark energy and dark matter. It's about 65% for dark energy and 30% for the dark matter.
Wow.
And it's only 4 or 5% for the normal stuff.
Yeah.
So normal stuff being, stars, gas, planets,
us,
things like that, light. But it's only 5% of the whole energy budget of the universe. So indeed, there are these things that really define how the universe is evolving, and we don't really understand them, either of them.
So you're not even looking out there for an answer. You're looking out there for possible ways of figuring out what the answer is. Like, will you, or do you think, is it possible that you could see something and go, oh, okay, there you go, there's our problem?
So for the dark energy, what we are trying to figure out with Euclid and other experiments that are starting both on ground and in space soon, this is really whether it's really just a cosmological constant or if it's more complicated than that.
Right.
So,
right.
Because one thing is we don't really know whether the equation of state, as we call it, of dark energy is changing with cosmic time or if it's always the same. So if it's really a constant, like lambda, a cosmological constant, then okay, that would be a result. That's our current model, the lambda CDM.
Right.
That's what Planck also contributed to establish.
Right.
And so with Euclid, you want to go further than that. You want to maybe detect or try to constrain this. Say, okay, is it really a cosmological constant or is it something more?
Wow, you've got to be hoping for that constant, aren't you?
So, people get excited when they see something new and mysterious. So if we start seeing a deviation from the constant, people get really excited.
That's true. Yeah, I guess that's true. Yeah.
A lot of work more for theoreticians.
Yeah.
There are many theoreticians and they always have a lot of imagination. That's not a problem. But so far, the data are still pointing to cosmological constant.
Right.
So far,
Okay.
there's no deviation. But yeah, maybe with Euclid, we will start to see something or not.
Oh, I can't wait. And when are the next images coming in? Is it March or they've come in and you're
Yeah,
looking at
in
them now?
March we have the release of three deep fields. We call deep fields. And so three areas of the sky that are quite good. We see a lot of galaxies in there.
Right.
And yeah, the good thing also is that we'll be able to see already some really old galaxies.
Yeah.
And so it's going to be really nice.
And there's already been some discoveries that have sort of gone, wait a second, why is that happening? Right? There's been a few sort of interactions of galaxies and stuff that you were like, that there was some question about. Am I right in thinking that?
You mean like interaction of galaxies?
Yeah. Was there some stuff that they were surprised? I thought there was some questions about how they were interacting or something, or maybe it was just the first time they'd seen them interacting. I don't.
Oh, I don't know. I mean, there are many interactions between galaxies, but yeah, this is well, it's not fully understood for sure. But this is for Euclid, it's not really something we look at.
Oh, okay.
Because
All right.
we really look at the big numbers. We just want to see so many galaxies. You know, but there are people that look more at the local universe, and they're looking at this what you're saying of the interacting galaxies. So how a galaxy evolves. So there's a whole branch of research that has to do with how galaxies change morphology with time. You know,
How stars are formed,
like irregular galaxies, and then they have star forming regions. They start making these spiral arms. They become spiral galaxies, and at some point after they have consumed all the gas and all the stars have been formed and then died, then the galaxy becomes more quiet and they become like elliptical, things like that. You know, the whole zoology, let's say, of galaxies. But this is something like not really the core thing of Euclid.
But it's but a side product, I guess, is that everyone is taking that. Everyone can look at that data and pull out their own little stuff.
So there are so many scientists, so many different types of astrophysics that you can do with different types of galaxies. Also, local stuff like even the solar system. They will also detect asteroids, new asteroids.
Oh, great! Yeah.
We're looking at so much of the sky. So,
what's your favorite? You got a favorite so far?
Favorites?
You got a favorite? You got any particular images or things you've seen so far that you've gone like, oh yeah?
For me, the favorite so far from Euclid was the one of the first images, the cluster of galaxies that you could see one of the first one before the 1% thing.
Yeah.
There was another press release, and then you had like 5 images, I think. Yeah, 5, and one was a cluster of galaxies.
Was that sort of almost like a string of pearls? There was kind of a
so you could see you could see many galaxies there, and you could see already from the colors you could see really different times in the history of the universe and different colors, so different age and different shapes of galaxies too. So everything was like already in that image, so that I really liked.
And it was is there any kind of I mean, they were breaking down the images. They had I guess when the first series of images came out, they had different experts coming in and talking about each sort of like the important part of that stuff. Your focus is on the mission. Your focus is on that. Do you have a specific? Your data is just about dark matter, or what is your specific focus for you?
For me personally, what I'm doing is I take care of the survey, so planification of the observations.
Okay.
So like the sequence of observation and this kind of thing. So because it's quite complex because we don't just go from one place to the next observing the sky. We also have to do all kinds of calibration stuff.
Right.
So we have to go to a calibration and then we go back to observing what we call the wide surveys. And then we also have the deep field that we are going to have this press release soon. So we also have to go to those areas regularly with the different angles to see the same thing with different angles and so on. Right. So there's a lot of different things that you have to put together to make a plan.
How many people are working on this? How many people do you have on Euclid? I mean, what's the roughly?
The scientists is like 2,000 people. It's really crazy.
Wow,
But
that's a lot of email.
Yeah, but you don't email them all together because they're like, most of these people, they work on specific working groups on specific science, like evolution of galaxies, one of them, some type like high redshift cosmology, like solar system, like so on.
Right.
So they're like, they have different groups, of course, and then of course you look at the data processing part. It's maybe, I don't know, maybe 200, 300 people, and I'm not sure, but quite a lot anyway.
That's amazing too. Like I've been playing with some. I did a Google Analytics course because I'm just fascinated. I always loved the idea of being able to sort of find patterns and visualize data and stuff. So the data that they're plowing through, what are they using to analyze that? How do they analyze it? Because surely if you're dealing with billions of galaxies, how do you possibly process this?
Yeah. So it's complex process. I mean, first of all, you have these images that they come from CCD. You have this kind of raw image. Mm-hmm. So you have to do something like similar to something like if you have a picture, a photo from your photo camera, and you're trying to make it better. So you have to remove some of the glitches, So this is like image processing in a way, right?
You're cleaning the data first.
Cleaning the data, you do it in a way that you try not to lose information, you try not to insert more artifacts or anything. And after you've done that, you have this what we call these calibrated frames, these calibrated images. And from those images, what you do basically is trying to count galaxies there and to measure how many you have, their positions, their colors, their redshift, their shapes, and everything. Of course, it's not humans being.
I was going to say it's got to be automated at this point, right?
It's all software, but it's really complex. And then from that, you have these catalogs. So you have catalogs of objects. So typically, then you will have information like their position, redshift, so on, flux and so on. And that's basically your main thing that you have for doing cosmology. You have these catalogs, and from that you're doing things like quite complex statistical things, like what we call the 2-point correlation function. So you have all these many galaxies that are in the sky. You're doing correlation functions, so it's something that it's a statistical way to measure how they are organized in the sky, how they are grouped.
Is that like you do random groups, and then the process basically starts grouping them into various different
So you're trying to measure basically how they are grouped together. This is something that will give you a lot of information about the universe. If you see them scattered a lot, simply speaking, for example, it would tell you maybe that the expansion was faster than what you expected, or something like that. Right. You understand? So every different statistical moment that you can measure will give you some information about what is happening in the universe. What are the parameters of the universe, like the density, the matter density, the total density, the cold dark matter density, and so on. Right. And also the Hubble constant and these kind of things. So all these cosmological parameters, what we call cosmological parameters, within the model that we have, that is the lambda CDM.
Okay. And then from there, people can then take that data and create their own simulations, or knowing that they've got the right data, basically.
Right. So, so the database from Euclid will then be used in other types of software to compare, this data to different models of the universe. Oh. So this is how you figure out, let's say, what models of the universe are more likely and others are less likely. So there are plenty of different models. So within the lambda CDM, you have all these small variations of the different cosmological parameters that you can have. So you have these huge, let's say, statistical hypercubes of data and simulation that you have, and you do basically what scientists we used to call chi-square. So chi-square is just like the chi-square is like when you do the difference between the predictions from your model and your data.
Huh.
You do it in a statistically meaningful way, so that's why it's called chi-square, because we take the difference of the squares and then it's just
And it
but it's
basically gives you an idea of how
basically
close you are to
comparing.
your model. Then is that?
Yeah, it's basically exactly. So it's comparing models to the data, and then from that you get a kind of a map in this hypercube of which models are more likely than others. So you have like this banana shape likelihood that then you look at and you say, okay, that's you say, for example, okay, the one of the conclusions possible with Euclid could be that the dark energy parameter that depends on the history that we don't know if it varies or not. You know?
Mm-hmm.
So that one, okay, it's likely that it varies by that much over that many billion years or so.
And so you can look at the data and go, does it fall within those parameters, or which ones fall in those parameters best? Wow.
So it's really a lot of work. It's really incredible data crunching, because you start from billions and billions of galaxies with all these different information points about them. and then you get down to like 4 or 5 cosmological parameters.
Right.
From that. So it's quite a lot of crunching, right?
It's amazing. The big thing I got from data analytics was the cleaning. I felt like all of your time goes on that cleaning and making sure you got the right data and getting rid of any data that you're not sure about and any weird little anomalies and stuff. It is amazing how much, like how time consuming that process is.
It's very time consuming, and it's also very error prone, and you need to do all the time comparing with simulations to make sure that you're not doing anything wrong. You're not introducing your own artifacts into the data.
Which I did a lot, by the way. I did a lot of that.
We all do.
Yeah.
When you do a processing, by definition, you will modify your data.
Right.
So you have to make sure that the way you're modifying it is not harmful to what you're trying to get out of the data at the end.
The number of times I found myself analyzing something, going like, "Oh, look at this! Look at that! Oh, wait a second." You go back and go, "Oh, of course I forgot to do this, or I overdid this, or whatever." Yeah, that's amazing. I mean, I'm assuming obviously this data this data will be compared to other data from other satellites, other observations and stuff as you go. How long does the Euclid program? I mean, I know how long the satellite lasts. The program itself, how long will that run for?
So the observations will be 6 years, maybe more. It could be a few more years if we have all the onboard consumable that are still good. In principle, it should be more than 6 years. It could be, we hope, 9 or 10 years in total.
Yeah.
Just for the observations, but then after that, so you still have some time for better data processing and the data releases and so on. So, I mean, in total, with all the preparatory work, so some people they started working on Euclid already, like in 2010 or before that.
Wow.
And it could go on until the mid-30s, like with all
the gift that keeps giving.
So it could be like some people work 20 years, 25 years on one mission. And it's not, it's kind of normal on this business.
And what's it like? I mean, what's the environment like where you're working? I mean, are you working with a lot of people, or I don't even know, like, what's a day like for you? What is a day working on Euclid like? What sort of stuff are you up to?
Being in front of my computer, doing things like planning the survey, of looking at what other people are doing, and answering emails and calling people, doing meetings to decide something or to react to something happening on board, because we have all kind of things happening. Like we have the sun. Like the sun is the problem, right? At the moment we are going into the maximum of the sun, so we have proton showers coming once in a while. That's not good for our detectors. So typically when there is a proton shower, then we have like 1 or 2 days maybe, or a few hours of data that we have to throw away.
Right.
So then we have to react to that. How do we plan to reobserve these areas? Do we want to do it or not? Is it useful?
It's like a scheduling nightmare.
Right. So it's like all the operational work, that what we call operations, is that we are like really like everyday work with having a spacecraft in space with all the environment of space. That is, that is the sun and the other things that can happen. So
And when you're checking in on Euclid, are you? I guess are there onboard cameras and stuff so you can sort of see where things are, and or is it all just data coming at you? Is it?
So we get the data coming once a day. We have
Okay.
fast, so we have this data that comes during about 1 hour. That's all the data that is taken on board during the previous 24 hours. It's coming through these big dishes, these big antennas that we have. So we have ESA has like 3 of them
Right.
on Earth, and NASA also has 3 or 4. I mean, there's a whole network of ground-based ground stations, as we call them. So that's how we get the data. Once a day.
And that's your data from the satellite, and also the data about the satellite, like how it's
so everything coming from it's science data. And it's also what we call the housekeeping data. So everything that tells you about the health of the spacecraft,
right?
Like temperatures and things like that.
Wow.
So everything comes once a day, and if there is something wrong, then we look at it and we react and so on.
And is when you say react and looking at problems and stuff, are you all sitting together in? I mean, I'm going from the Hollywood side of stuff. Is there is there a control room where you all sit and discuss these things, or is it all just done separately?
Oh, I wish it were like that. I mean, I wish it were like in the movies. It's more nowadays. It's more like all virtual. It's like Teams meetings.
Really? So it's all remote. You're doing it remote.
Yeah, mostly. I mean, sometimes we have face-to-face meetings with people.
Right.
But nowadays, most of the time, it's just calling people on Teams and this kind of thing. So if you come to the place I work, the ESA near Madrid,
I'd love to.
You will see that there is actually one place that is kind of look like a control room in like the movies,
right.
It was in the old days, because this was working more like this, like 20 years ago.
Right.
That was more like having this control room from, and you had really.
I guess you needed that. You needed that.
So you still have that.
Yeah.
You still have that, but most of the time, to be honest, the room is empty nowadays. So people work from their computers, from home or from their office. But
I went to JPL, and they've got a nice setup that looks very. It looks very spacey. They've got it, they've got that. But I got the same sense that there were a few people there, but it was, I guess it makes sense. I'm both sort of, that's both depressing and also exciting to me, because I go like, okay, so you don't have to be there in special jumpsuits with badges and stuff. This science is happening. This is happening everywhere. So, I mean, I think that is such a huge plus, I'm sure. I mean, it feels like it's opened up to more people because of that.
Yeah, it's more practical, but on the other hand, I think it's a little bit less exciting.
Well, you could get a jumpsuit. You could buy like a jumpsuit and put some badges on it and stuff.
Wear the cosmonaut suit.
I'm sure no one would tease you about that.
Oh, they would like it, I'm sure.
Yeah, there you go.
One day. I should do that.
Yeah. That's interesting.
Get that on Amazon.
So your day is basically is the computers and emails and meetings.
Yeah, basically that. Except when there is like a face-to-face meeting somewhere, or sometimes we travel to some other place for a conference or for a meeting of some kind. But yeah, that happens maybe for me like 4 or 5 times a year.
Right.
Some people more important than me, maybe they travel more, but
right. And so okay, so and how long have you been with Euclid? Because you were before you were.
So since 2016. So.
Oh, okay. All right.
Almost 9 years now. Yeah.
And how did you? Let's go way back for a second. How did you get into this? What was the impetus for you? Were you a little kid looking up at the stars?
Yes.
How did it,
Yeah, I should say yes. I was a little kid looking at the stars. That's true. I was really all the time interested in that. So I really like to look at, physically with my own eyes, look at the stars. I also liked a lot to read things about the solar system, and so I started with that. So I was really excited about things like galaxies, and just the first thing that's striking, I guess, when you look at that as a kid is just the sheer size of things. The universe is huge,
Yeah.
right?
Yeah.
It's just impossible to fathom the solar system by itself
Yeah.
is immense, right?
Just
And then
our
you
night
start
sky's
at
enough. I mean, yeah.
yeah. So then you start realizing that beyond the solar system, there's the whole galaxy, and then there's the whole universe around. It's just like so fascinating. So yeah, that was the thing. And then when I was like in high school, I really liked physics. I mean, physics was really something I really enjoyed because I really, the satisfaction of understanding how things work.
Yeah.
How actually the world is made of, the stuff that makes up the what we are as human bodies and the things around us, and why the apple falls from the tree, and then
Right. Right.
so then I was like with these two things, like this curiosity for astronomy in the first place, and then really the physics part, and that what
It's a good combo.
kind of
Yeah.
I wanted to be an astrophysicist.
So you just pursued it just straight out of high school. That was it. You just went straight into it. That was your.
Yeah, then I went to physics to the university for physics, and did the PhD in astronomy, astrophysics, and yeah, that was
Wow. That's a lifelong goal. Like that's literally that's it's been the stars the entire time.
yeah. I guess you could say that.
That is fantastic.
Yeah.
Wow, because that's not that. I mean, it's amazing how rare that is when I talk to people. They usually sort of start in one direction, and I mean, there's a lot of the Earth observation people who start going that way, and then they go, "Oh, we need to look at the Earth," and there's a lot of sort of happy accidents. But I love that. I love that child focus of like, "Oh yeah, I want to know. I want to understand this." Like it's funny. My fascination with the space stuff was always, I loved all the images of space. I loved all the rockets and the astronauts and all the excitement, but my interest was always in the computers. It was always in the computer side of the stuff, because I was fascinated by the technology of these things rather than I was never brave enough to think I was ever. I don't just play a coward on television. I'm happy to avoid any danger. So I had no interest in going out there. But the idea of how you figure this stuff out, how we make it, how we compute the process of these things was always fascinating to me. We should go to some questions because I'm seeing a lot of chatter here.
Okay.
I will say this to everyone right now. I apologize. I'm not really getting to the chats because I like to focus on our fabulous guests, and I feel like this is an opportunity I'm very lucky to have. So I'm using that as much as possible. But we will go to some questions now. Let me just check in with Agna and see if we've got any questions. You can grab grab a coffee or something while if you need a break. Thank you so much for this. I'm so enjoying this. And the Euclid program, I will say this to people again, go to ESA, check out the stuff they've got on Euclid, because it's exhaustive. There's the most amazing stuff. I was doing my burn and learn yesterday, and on my little rowing machine, listening to all these wonderful stories and looking at these amazing images. So there's just some amazing stuff out there. All right, let me get into some.
Yeah, there's a nice movie. So.
Oh yeah, no, there's a nice documentary on it.
There's this short movie about what we talked at the beginning, and there's 1% of the survey.
Yeah. Yeah, they've done a really good job of it. I'm surprised. Like, it's funny. I see NASA all over the place. ESA, for some reason, I guess it's the European way. It's not quite so sort of in your face or something. Like, it's just, you have to sort of seek it out. I find.
We're slow learners, but I think
You're getting there? You're getting there now. All right, I'm in the wrong email, so let's check this. Agna, of course Agna's come through. Okay, we got a bunch of questions for you. You ready?
Yeah.
Here we go. So Lisa B. Hello, Lisa B. says, assuming unlimited funding. Ooh, that's always fun, isn't it?
Nice.
What would Dr. Dupac's dream study experiment project be?
How the matter organizes itself in the universe during that time is to observe what we call the hyperfine transition of hydrogen. But it's a very, very weak line of the atomic hydrogen. And for that, you need an incredibly sensitive type of radio detectors. And that would be really amazing if we managed to observe that with precision.
Are
So
there
that
any
would be
plans? Are there any plans for that yet?
there are many ideas. There are many ideas, but the funding is and the technology is the limit.
Right. Okay.
But that would be really one avenue to pursue. And the other thing that's even more difficult is the neutrino background.
Huh.
So the neutrino background is the cosmic background of neutrinos. It's a bit the same thing as the cosmic microwave background, only it's not light, it's neutrinos. So neutrinos are these funny particles that are not really interacting very much with the rest. They do, but they're not so much. So they are difficult to detect. So they have been detected from Earth, but coming from the sun.
Right.
From the sun, there are quite a lot of neutrinos coming from the sun. So it's possible to detect them from there. But to detect this background coming from the very early universe, it was way before the cosmic background. I think it was maybe in the first seconds or minutes, I forget. But it would be really like looking at the very, very beginning of the universe, just after the Big Bang. So that would be something absolutely.
How would you do that? How would you?
For observing neutrinos, you have these big water detectors.
Yeah.
So you would need something like that, but a lot more. So you would need to go maybe to the moon to bring I don't know how many billions of liters of water there to dig and to put a huge. I mean,
wow.
You
said unlimited funds. That's true. No, that's true. Yeah. Well, could you use like the water in one of these planets or moons we've been exploring? I mean, would that work?
Oh wow, that's a great idea. Yeah, you could go to the moons of Jupiter.
Yeah.
It's ocean below the ice. So you could go to Europa or Ganymede and
check
one of
out
them and do some kind of.
It's a lot cheaper than hauling water into space, I would think,
That's a great idea, actually. I think we should really think about it.
Problem solved. We'll start a Kickstarter.
Problem solved. So just
we'll do a Kickstarter, a GoFundMe, and we'll have it sorted in no time.
Yeah.
But basically, isn't that like we do the similar kind of stuff here, don't we? Don't we have these sort of caverns of big giant cement caverns underwater that are used to detect these things, right? Isn't that the?
Yes.
Yeah.
Yeah, but it's not enough to detect the background coming from the universe.
Right.
So you would need to do a lot more, and also there are different. There are low energy, so I mean I don't know. There are lots of technological challenges involved, but it would be another interesting, very interesting line.
Yeah, that's fascinating. Wow, really? I could see scientists getting excited about that. I guess it'd be hard to convince people. I guess how difficult is it to convince like governments and organizations to pursue things like this? I mean, is there a lot of pushback saying like, why do we really need to know what dark matter is? Or I mean, or do you think we're in an age where we're feeling like that? Although I suppose that could change, but
Yeah. So I mean, normally, if you can sell your project like something that is going to bring something back immediately, then it has better chances to go through.
So Euclid's perfect because you've got beautiful images coming in very quickly.
Yeah, but I mean, if you can sell them things like more like technology, or if they think that it's going to bring money and investment and so on, then it's a lot easier. So for fundamental science, like what we're doing, we rely on, let's say, pure interest from also the politicians. Say, okay, this is pure research. It's like it's part of, let's say, culture, human culture. So it's something important because we want to know where we're coming from. We want to know where we are, what the universe is, and this kind of thing. So
that's fascinating.
It's kind of it depends a little bit on the politicians that are in power also.
You raise a really good point, though, because I think we've hit on the difference between the American approach and the European approach. I feel like Europe approaches space exploration like an art, like something that needs to be funded, that something is, that needs to be nurtured, that needs to be, whereas America is very much, as you say, it's very much about that, hell yeah, we're going to to get to Mars. We're going to do. It's not, you know what I mean? Like they sell it in a different way. But there's definitely a sense of it reminds me of. It's funny, just as you said it, it reminded me of film, like how Europeans tend to think of film as an art form in Europe, whereas in America it tends to be a business, right? It's a very different.
Yeah, but I also like sometimes the way the Americans are doing it, because I mean, at some point there's this huge enthusiasm of like we go to Mars,
Yeah.
and we plant back there, and it's really everybody just is crazy about it.
Yeah.
And I think this is also good. It's really at the end it's a human adventure, and it's I think it's right. I mean, there's real pride to have to do these things. I think the Apollo program was really such an incredible thing.
Yeah,
And they did it, and it was. I mean, and I think the American people should really feel really proud about it.
Well, we're pushing ahead too by the sound. Sorry, I say we. I am American, but I'm also a Canadian. I'm a Canadian American and a Brit, so I've got them. I got them all. I got to figure out how to get to Europe now, though. That's my next thing. All right, I'm sorry, I've completely gone off topic. Thank you, Lisa B. All right, Geekabibble. I love the names. So, would there be dark matter, energy, galaxies, and creatures, etc.?
So you mean could there be life made of dark matter?
I guess so. Yeah, energy, galaxies, and possibly even creatures. Maybe is that a
So
possible?
it's very difficult to imagine, because dark matter is just not interacting at all with light. So life as we know it, well, say as we know it, life is really depending on the electromagnetic force. Everything is electrical in our body. And everything has to do with atoms that are glued together because of the electromagnetic force and between the nuclei and the electrons.
It'd be a fun sci-fi.
Everything chemical is exactly the electromagnetic force at play. So dark matter is nothing like that. So you can maybe imagine something different, completely exotic, but yeah.
It's in the realm of sci-fi for sure.
Yeah.
Okay. It would be an interesting thought puzzle, though, wouldn't it, to sort of try to figure out how it would work if that, all right, Geekabibble, good question. Oh man, this I don't even know how to say this. Kaelanthelian says, is the presence of dark matter and dark energy the reason why space isn't absolute zero in temperature? Let's start with that one.
No. So the reason why it's not absolute zero is that the universe is not. It has started at some point in the past. That was 14 billion years ago, so what we call Big Bang. So it's not. We know that the universe, in this respect, is not eternal in the past. So if it were, if there were an infinite amount of time that had occurred since the beginning of the universe, then it would be zero, because let's say the expansion would have been infinite already, but it's not the case. So the space temperature is 2.7 K. That's the temperature today of the cosmic background,
and that's just
it will continue to cool. So if you look at the far future of the universe, it will eventually get to almost zero, and never exactly zero, but it will get to like as close to zero as you want, but
eventually
in a very long time. Eventually,
okay. All right. Okay. And then the last part of the question was, or does dark energy have no measurable transference into heat energy?
Right. Not at all. Because, the dark energy is something, it's very mysterious. It's something related to the volume of space. So sometimes we call it vacuum energy, because it seems to be like it's growing with the volume of space, so with the void. So the more space there is, so the more the universe expands, the more dark energy there is. And this is different from matter and normal energy that gets diluted when space expands. Yeah.
That is really a
kind of weird. It's really weird.
Twister, yeah. So basically, as things pull apart, it's not stretching, it's filling in the gaps.
Right. So it's the space is stretching, but at the same time it's stretching, there is this mysterious vacuum energy that is kind of created out of nothing. It's really weird.
You don't
and we're
think we're
trying to
missing
figure
something? You don't think there's nothing, we're not missing a factor, a gravity factor or something? There's nothing you can think of that would.
So some people indeed, some people who don't really believe in dark energy or dark matter, they try to work on what sometimes is called the modified Newtonian dynamics, just alternate gravity, that is modified the equations of gravity to try to explain what is happening in the universe without having to invoke these artificial things like dark matter and dark energy.
But
So
no
there is a lot
success
of
yet.
it's not really successful because it's very difficult to explain everything at different scales with this. Because the dark matter, you need it to explain the curve of the gravity curve of galaxies. You need them in the clusters of galaxies too. You need them at the cosmological level. So it's really, really hard to get rid of them.
No, it's fast. It's a fascinating problem.
So it's still an open issue.
I'll find that video I watched last night. But there was a theoretical cosmologist. Or maybe she was a cosmologist, but she's dealing with theoretical. I guess if you're dealing with theoretical stuff, anyways, I suppose. But I'm
an observer.
Yeah, exactly. Right. But what she was saying was questioning whether gravity is like our understanding of gravity right now is that we've got our two planets, no matter how far apart they get, or galaxies or whatever, no matter how far apart they get, there's a sort of a gravitational effect on them. But that potentially gravity could actually not be infinite. That maybe there's a drop off, and that could help us with. But it's so funny because it all just comes down to math. Basically, right?
Yeah.
I mean, unless we can see something to prove any of this stuff, it's all just numbers to make it all work out, right?
Yes, but this is exactly what these people are working on. So trying to modify the law of gravity. So so that after a certain scale, a certain distance, there's no gravity, or it gets smaller than what we think it is.
Now, do you ever get? Sorry, I'm going to go off track again for a second. You're there. You're handling the Euclid stuff. Do you ever just go like, screw this? I want a telescope. I want to go outside and just look up at the sky. Like, do you ever get that? Just want to see something like?
Yeah, but I do that at night. Sometimes I go just out of the house and just watch the sky. At the moment, it's really beautiful.
Yeah.
Have all these planets visible together.
It's strangely clear
Jupiter,
here as
Mars,
well.
and Saturn. So
do you have a telescope? You have a telescope you use it at home?
Actually, no, I don't have. I have binoculars.
Yeah, binoculars. I found binoculars really useful, actually.
Yeah.
The telescope I found sat around a lot, getting dusty or getting knocked over. So the binoculars just tend to be that's interesting. Oh, good. Okay, so I'm in good company then, looking up at the sky with a pair of binoculars. Okay, all right. Kaelanthelian. I'm so sorry. Whatever wonderful name you've come up with, Kaelanthelian or alien says. Do you think? Oh, I don't know what that means. Do you think WIMPs, WIMPS, or macho, MACHOS, are better explanation for dark matter, or is there something else? Would you mind explaining those?
Yeah, WIMPs, so weakly interacting massive particles. So this is a class of particles that theoreticians evoke when they try to find good candidates for the dark matter. So there is a lot of work like this. So because since we have no idea what it is, only we know that it cannot be baryonic matter, hadrons, so things made out of normal quarks,
things
made out of normal protons, neutrons. So it can be some other things. So it can be. So sometimes they work with the supersymmetric particles. So supersymmetry is something that is not, let's say, proven, but that could exist. So these are kind of exotic particles that you can have that could be used to make dark matter particles. But so there's a lot of research on that. For the machos, there was at some point a lot of work on that.
Sorry, what is a macho? What's the macho?
The machos was I forgot the acronym, but it's more something about the brown dwarfs and these kind of things. That would be like normal matter, but you wouldn't see it because it's not emitting a lot of light, like a
Right.
brown dwarf, large planets, free floating planets,
Right.
things that you wouldn't see in your data because you see mostly stars and gas,
Right.
but that would be there in large amounts so that you could explain the missing matter like this.
Oh, okay.
That
All right.
nowadays is a lot more difficult because I mean, the numbers are not just there. I mean, the dark matter that you need is so huge that you can't possibly form that many matches to explain all that. I'm not a specialist of that, so maybe I'm saying stupid things, but I would think matches it just doesn't add up.
Right. Okay. So you prefer, if anything, you would prefer the WIMPs, the WIMPs.
The WIMPs is definitely there are.
But you'd have to detect those particles, right? Those massive particles.
So you would also need to be able to make them in the lab, in these big colliders and things. But also it's very difficult if you don't have enough energy to make them. So.
Right. Oh, so you'd need massive. I guess you'd need incredible amounts of energy to make something like that. I'm guessing.
Yeah.
Okay. All right.
Yeah, depending on what kind of particle, it's different. So, but
Next question. Could neutrinos be dark matter in some way? Are they connected in any way?
So neutrinos, they cannot be called dark matter. They're not really dark matter because they do interact with,
we can detect
with the normal matter. So yeah. So,
it's like, what are we missing? Everyone's looking for, like, what could it be? There's got to be something, because it just feels like.
That's the thing with the normal particles that we know about. It doesn't really work, right? Dark matter, so you really need to invoke exotic stuff.
Here's a good question. Is there a sci-fi movie that you love? This is great. So one you love, one you hate. Is there are there ones you go like, come on, and then there's other ones that you're like, you enjoy, or shows for that matter. I guess.
Yeah. So I really liked, for example, Interstellar. I really liked.
Yeah.
Even though there are things that are not really realistic.
So many things. Yeah. Yeah. And
but overall, I mean, it was really good. I think there are lots of things they're trying to talk about. So many things like the future of the Earth and the gravity, the way to solve gravity and so on, and the black holes and space travel, time travel, all together.
Yeah, I'd argue there were too many things. Maybe they should have focused on a couple. Yeah.
Normally I don't like too much when there's time travel to the past because there's all getting into paradox.
Yeah, the paradox kills me every time.
It gets impossible, but in that case I really liked.
I have to see it again. My son keeps talking about it because he sees clips of it on TikTok or whatever, and I feel like I should give it another chance because I watched it and I remember being completely captivated, but it just went on and on and on. I mean, it's just too long.
Yeah,
all right,
that's right.
Well, that's interesting. So Interstellar was kind of the movie that both you loved and hated at the same time. There were things.
No, I didn't hate at all.
Didn't hate. Oh, great. Oh, good. Okay. All right.
Even though there were some not realistic stuff, but that's part of the.
Any movies that you go, oh man, if it wasn't for that movie, I wouldn't get asked these stupid questions all the time or whatever. Is there?
No, not really. I don't really see.
No, nothing.
Yeah, I mean, normally I like the ones that are more realistic. So, for example, like also
The Expanse.
And that one I think I haven't seen.
Look, my friend did the visual effects in the first couple of years, and the effects are gorgeous. I watched the first 2 seasons, but everyone loves the show, like absolutely loves the show. So I feel like I should delve into that. But yeah,
I mean the ones I liked a lot, but it's not realistic. But I love them is Dune. I mean, both the new one and the old one.
Oh my god,
the old one by David Lynch. I really love it.
Really,
there
were aspects.
Stuff,
I really, you know what I miss? You know what I miss in the new ones? Is I miss those giant floating beasts that do the navigation.
Yeah.
I miss that.
Yeah, the navigators, the guild navigators.
Yeah, so cool. That book series was it was one of those. It was like amazing. That and Neuromancer. Neuromancer was the other one that I read, and I was like, oh my god, I just want to live in that world, even though it's miserable. I think it's part of the problem with all the billionaires out there now. They all want to live in these movies that they've seen, but they're all nihilistic. These terrible worlds where it only rains. Okay, other questions. Sorry, I'm being really selfish and stealing all the time. Okay, Lisa B again. Yay! I live in Hawaii. Oh, what a flex. Okay, so Lisa lives in Hawaii. Good for you. They've been trying to build the 30-meter telescope here for a while. What makes it so special? Will a telescope like that bring some new capabilities in monitoring space?
Good question. I don't know much about this particular telescope.
Mm.
Is it the one they're trying to build on IKEA or?
I think there's some issues, but they just don't. Basically, people are saying like we just don't want a giant thing built on.
Yeah.
Um, it's a tough one, isn't it? I mean,
Yeah, I don't really know much about this one.
Okay, all right. So, and then another one of my favorite questions from Lisa B. Will AI, it's always got to come up now, doesn't it? Will it be used to process and understand the vast amounts of data? How useful is AI going to be for this stuff?
Yeah. So at the moment, we use AI like what we say machine learning algorithms. So typically to do things like, for example, for this business of cosmology, it's used a lot for galaxy classification. Typically, the kind of thing that you can you can really make use of AI to analyze the data, to classify things. So the AI would learn how galaxies categories are like, and then they would from that they would get a data set and get all these galaxies into categories and so on.
So some of the grunt work will be covered by AI then, for sure.
Yes, and it's increasing. It's really getting. Actually, I was at a conference recently, a few months ago, and cosmology conference is crazy. Like half of the talks were about machine learning and AI. While like maybe 10 years ago, it was like there was one or two. Like, it sounded crazy, you know?
Yeah, the problem is it seems to be, I think people are so enamored with the technology that they forget it's a tool, and it's not like you're not going to use a hammer to try to screw, put in a screw. You know what I mean? Like it's like this. I feel like there's everyone feels the need to throw AI into the mix just to sort of show that they're that they're hip and cool, but it does it has its limitations for sure. I see it a lot in the film industry as well, because the film industry is sort of reeling because it's able to do so many of these things. But so are you using AI at all yourself? I mean, do you use it in your day-to-day work? Does it help at all?
No, myself, I haven't used it for the Euclid work, but it's getting there more and more. So
it's fascinating, isn't it? I mean, I use it a lot I found it incredibly useful for programming. It's very, very good at programming because it's just syntax, right? It's just instead of having to look up those clips of code, you just ask it and you can run stuff and you can actually get it to debug and stuff. Right? I found that really useful, and organizing stuff. Just organize, like if I've got a chunk of stuff that I've just gone, I've got to remember all this, and then have it organize it for me is fantastic. I find that amazing. But there's no sort of, I guess there would have to be policies in place for using this stuff too, right? ESA's got to have, because you don't want people just sort of using AI and then not knowing how they've got the answers they've got and things, right?
So in science, I think at the moment it's getting really like what you're saying is that people make papers based on AI, and they describe the way the machine is built and then learning things a bit. But you actually, that's it. We lost already the connection. I mean, the machine gives you the conclusions, and that's it. I mean, I think it's we're already there. We are already at the point where we are already not really understanding what the machine is telling us.
Yeah,
already.
That black box problem that they have is,
the black box
is an
thing,
issue.
it's going to be more and more of this in the coming decades.
We definitely live in interesting times when it comes to the AI stuff, for sure, and also misinformation.
You know what Stephen Hawking said, right? That AI will be the greatest invention of man. The problem is it will also be his last.
Which is funny coming from a guy who used a lot of predictive, like all of his communication stuff was predictive, right? It was basically like, it was trying to work out what he was trying to say to speed up the process. I mean, that's fascinating. It is. It does worry me how many very smart people are concerned about it, because I don't see it. I just don't. It doesn't. the concern isn't there for me, but I tend to be a bit of a tech optimist anyway. So no.
Yeah. So I'm a bit concerned, not
Are
for
you
now, but
really?
the 50 years from now, because it's not only being concerned in the sense that machines are going to take over and kill us. It's also concern in the sense, already nowadays, for let's say translators are out of the job already because AI is doing it.
Programmers. They'll be next.
Programmers. 20 years from now, 30 years, maybe, novelists, screen directors, actors for sure. You name it. I mean, we will all be out of the job. So what are we going to do? Are we going to sit and enjoy, or what will happen?
Yeah, it's funny. I feel like there was a wonderful quote about it, which really got me. Was someone said, I want AI to do my laundry and my dishes so that I can do my writing and my art.
That's the thing then.
But I think that just because a tool can do it doesn't necessarily mean there's going to, I mean, like I think there's always going to be a human. This is why I feel like this is why I love this whole I'm a genius thing, with the idea of like sitting down and talking to people and putting a face and a personality and a passion behind what people are doing, because science, tends to be press releases and and the reality is there's people making this stuff, and the people are the creative part of it. This technology is all just tools, right?
So you will still be able to act in a film and to do your own art and your own writing. But if the writing by the best human author is not good compared to what the AI does, then what does it mean?
I know. No, I struggle with it.
It's a real question. It's a question I think we should all ask ourselves as in our democratic societies. Maybe there should be some debate about it. Because I think AI is incredibly useful for so many things, but there is definitely this question, I think, of what the place of human work and human activities in this.
I found it fascinating because what it did to me was, especially in the image generation stuff, where it can create, where like Stable Diffusion or I was using Midjourney for that. It can come up with these really nice images that are based on every image that's ever been made, and it made me question what was human about creativity, because I found myself going like, wait a second, like, is creativity really just us taking the stuff that we know and just going, mixing it up and then putting it out in our own way? Because if that's what creativity is, then yes, a computer's going to be much better at it, because it's going to have a much larger not experience, but a larger, volume of data to work with. It's fascinating. I mean, it's a real, like, we're at a really interesting point and potentially, as you say, potentially disastrous point for humanity. But let's go back to you for a second. If you were starting today, you're a kid, you're looking up at the skies, you're thinking, oh man, I want to know about that. What is the path people take? I mean, were there things that you did that helped your process or hindered your process? I mean, what does a kid do today to get into ESA, working on these kind of programs?
Well, I think basically, if you're interested in something, just read about it, just do things and don't overdo it. I mean, don't try to do things, do more than you can. But the essential thing for me, it's always been like the interest that you have, the passion. If you're really interested about something, just read about it, talk about it to people, and then if you want to become a scientist, then okay, you should study and should go to the university and get a PhD. So it's a lot of work, but it's also a lot of fun. So, and don't be afraid of anything. Just go for it.
Yeah, fantastic. I mean, that's it. I mean, like my Tech Bandits thing, I do this thing where this sort of education thing for kids, and my obsession is, like, I feel like all of the information is out there for people. Like, you can go to YouTube, you can go to the internet. The entire collective knowledge of the human race is available basically for people to look at. We just have to inspire the kids enough to want to look at it. I mean, you know what I mean? I mean, I know there's some misinformation out there as well, but the fact of the matter is, I think if someone, as you say, if someone's driven enough, they're gonna do it. So what about off time? We were talking before. Some opera, some chess. What do you like?
Yeah, I like to sing, so sometimes yeah, I sing.
And what are you singing? What are you doing?
Yeah,
Taylor
so
Swift? Any Taylor Swift?
no, it's just classical stuff. So
Right.
opera songs from 19th century song I like a lot, and these things. And but
So what do you do? So
uh,
if you're doing opera singing, what do you like? Are you doing this alone? Are you doing this with like? Do you put on? Are you in operas? Are you in like? What do you do?
sometimes I was sometimes yeah, sung with like local productions of opera, and
Fantastic.
sometimes just with the pianist, sometimes with all the singers, like a cappella singing as well. So
Did you
it
train?
depends.
Do you train, or is this just a hobby? Or
Yeah. So actually, I was when I was when I was a kid and teenager, I also studied music.
oh wow,
So when I was like 17, I kind of decided, okay, I'll give priority to science studies. So
yeah,
I didn't pursue much in the music, but I continued like when I had time to do it, and so yeah.
well, that's great. And
But
are you writing your own stuff as well, or is it all uh,
I'm composing a bit. Yeah.
fantastic? What do you compose with? What do you is it piano or what's the? How do you?
As so far what I composed is choir music.
Oh,
So
great. I was a
yeah,
choir boy back in the day, years ago.
great.
Yep, yep. Oh, uh, from everyone in the email. Oh, sorry, more in the email. Let's have a check.
Well,
Have a little check here. Oh, I don't see. Uh, no, did I miss something? Let me just get into the actual Zoom chat and see what's going on. All right. Did we miss something, Agnes? Is that? Let's have a look. Let me see if I can do this without. I think we're good. All right. I fixed my name. So the questions were coming from Kalen the Alien, but it was all one word, so I was trying to pronounce it as one. So that's it. Did we miss any other questions here? It's very interesting listening. Thank you, gentlemen. Lisa B is enjoying herself. All right. What do we got? Ooh. Oh, this is a good one. Nixie's got a good question for you. What advances do you hope will happen in your work, in the next sort of 5 years or so? Are there any sort of like big advances that you see on the horizon that you're excited about?
Okay, in the kind of how we do the work, and for sure, as we commented, the AI is something that's happening at the moment. So
Mm,
you can expect that maybe 5 years from now it will be for sure bigger than now,
a
and
bigger
that will
part,
continue
right?
to grow. Like in terms of advances in the science, I would say 5 years from now we should already have some good information about the dark energy equation of states. So stay tuned, because I think it could be really, really interesting. So with Euclid, we'll have the big cosmology release already, the first one in 2026
Right.
October. So that should be the first time where we have really the cosmology results. Also already some information about that, about the dark energy.
Are you
I
privy
don't
to
know
that
yet
stuff in
how.
advance? Like, do you know? Are you? I get
Yeah, I will know
no
maybe a year.
spoilers though, right? You're not allowed to.
I
Is
will
that
not be allowed to tell that
right?
to you.
Right. It's got to be so
Spoilers.
tempting, though, isn't it? It's got to be like you're sitting around
Yeah, but
singing some opera, playing some chess, and it's like, oh, by the way, what's cool? Um,
yeah, but the thing is, it's really the work of so many people. So,
yeah.
so they all deserve that they get the credit at the same time, and
Right.
so it's important to respect these things.
All right. Let me see what else we got here. Okay, so that's that chat. Let's go to this chat. There's too many chats. I can't keep track of it. Okay, let's see. DM detectors. Anyone wants to use AI? Job there in society. Okay. Oh, there's a lot of people talking about AI. Interesting. There's a lot of people. Hello, Deadly Crichton Citrus. Deadly Citrus. Sounds perfect for me. I'm just gonna just double check. Let me just pop in and make sure that I'm not missing anything on from Agnes here, because I did see something from Agnes. Everyone, two questions. There you go. I sent 5 more questions in your email. Okay, all right. Let me just check. I didn't see them show up, so let me just double check that again. We go. Inbox. There, oh my gosh, there you go. You got more. Okay, right. Is Euclid? Sorry, you okay to go for a little bit longer? How you feeling? You're not.
Yep.
Yep.
Yeah, good.
Okay.
Cool.
Lisa B says, is Euclid expected to provide any info further proving, refining, or even challenging the lambda cold dark matter model?
Yes, exactly. So that's one of the main things for Euclid. One of the big questions is whether it's really a lambda, cosmological constant, or if it's something more complicated.
Right.
So if it's just a lambda, okay, then we will just confirm and give better precision on the numbers. But if we do detect that there is a deviation from the lambda CDM, so for example, that the dark energy equation of state changes slightly in time, that would be something new. That would be kind of a revolution, really, for our field.
We get the math out. We're going to need it, you know?
Yeah.
Okay, so Kale-anth Alien asks, this might be a silly question. There's no such thing as a silly question. That's my job. Do you ever compare your modeling of universe expansion to astronomical evidence in archaeology? For example, the knowledge of ancient people about astronomy that can be discovered in archaeological findings? Or is it too unreliable compared to the data modeling today?
We don't really do that because, as we understand it, in the ancient times, the knowledge of the universe was limited to what is our solar system, really. So,
how far back is the data good? How far back can you get sort of reliable data?
So there are actually some things that we do look at in the archaeological records. For example, these are for the comets.
Oh, right. Yeah, of course. Yeah.
Yeah. For example, we know that what is today the Crab Nebula, the Messier 1 object, one of the most famous objects in the sky.
Yeah.
This was actually, so there's nothing to do with a comet. I'm mixing things a bit, sorry.
Okay.
This one was a supernova, sorry. This was a supernova that exploded in the, I think, 14th century.
Oh, wow.
That was recorded, and it was really very bright. And it was like visible during the day as well.
Oh, wow.
And for comets, yeah, because some comets have long periods. So they have come maybe sometime during the Middle Ages and so on, and then came back and so on. So it's interesting to see the records so that we can understand their periodicity and so on.
Right.
And then I'm trying to think about other things. That there are actually people who are specialized in that doing historical astronomy. Yeah.
So like they're looking at like cave drawings and going like, hey, look at that. It looks like a meteorite. That must have been about, whatever, or a comet or.
Yeah. So it's not really for cosmology because this was not something that was really observed earlier on, but for many things like comets, supernovae, also the cycle of the sun, because because the cycle of the sun has had consequences on many things during centuries, like when there was a colder period, there were more problems, people dying of hunger and so on. So this is a whole field of study. Actually.
Wow, boy, talk about niching down. Okay, good question. All right, so Nixie, you said you use binoculars, which are fine for stargazing. What magnification do you think is best? That's a good one because at first I was way too zoomed in and I was not enjoying the experience. I found keeping back a little bit was for me.
Yeah, I actually have no idea. I'm really an amateur on this, so I'm just, looking at things. I like to see the satellites of Jupiter and the moon, and that's basically what I'm doing. So,
what do you think of? What do you think of Starlink going through every so often? Does it bother you, or is it?
It's not so often, so it doesn't really bother yet.
It's funny. It really got me thinking because I was up at the cottage and it's a beautiful, starry night, and you could see this sort of string of thing, and I thought, he just changed the sky. You know what I mean? Like
it bothers people who try to take pictures with a long exposure.
Right. Of course. Yeah.
And you really have to know when they're going to cross with this big train of Starlink things and avoid these periods and. Yeah, but I think it's not so bothering today, but maybe in a few decades, it will be really bothering.
Yeah, it's funny. My son just said I was old because I was like an old man complaining about they didn't used to be. That change is the only thing that's inevitable. So of course. All right. Shelley de Cellier says so. Quantum entanglement cannot explain dark matter.
Wow.
Well, that was the Higgs boson, wasn't it? Wasn't that all about that? Wasn't that about the energy?
Quantum entanglement could explain dark matter. I have no idea. I mean,
that may be a question for
our... to think aloud, but maybe not. Sorry, I really don't know enough about this.
We've got Lisa Werner is coming back. Our quantum queen, who works out of Germany, and she's I can't remember the name of the place she works, but she's we'll have to Shelley, we'll have to ask Lisa about that. And then what advances? Oh, we said that. So we said what advances? Let me just check. See if I can let you off the hook yet or not. This has been so much fun. I'm just thoroughly loving it. Oh, yeah, there are more. You okay? A couple more.
Yeah.
Is Euclid expected to provide, this is Lisa B again, is Euclid expected to provide any further proving, refining, I've got the same thing twice. We've got it twice. I've got the same email twice. It's fine. Okay, well, I said let's wrap it up then. Let's let you go. I can see the sun changing behind you, so, what time is it there? Where are you at?
It's 5:45 now.
5:45. Oh my God! You got to get out there. You got to go.
I'm good. We can go on if you like.
Well, let me check a couple things with you. First off, you say you have a YouTube channel where people can actually hear some of the singing.
Yeah, but it's mostly about singing. Yeah, it's not so much about science. But
we've got a really fun, eclectic bunch of people. I bet you there's probably opera singers already in the chat. If there's any opera singers, let us know. But definitely. So I'll make sure we get that. We'll get that link in the description for people. And also, you said you were streaming. You were streaming chess as well. Were you playing chess?
No, I'm not streaming. I'm just watching sometimes.
Oh, I see. You're picking up some tricks. Yeah.
Yeah, I play chess sometimes online, but it's...
Any other games? Are you playing any other games at all? Or...
I used to play some video games. Now I'm mostly playing chess when I play.
That's good. That's good. Well, I mean, it's the video game stuff I found. Yeah, my problem is motion sickness. I can't. The games are getting so good that I feel sick when I'm playing them. So I tend to prefer that. And then what about and any science fiction you're watching right now? Any shows? Any sci-fi shows? You're watching Foundation or anything? Or
at the moment I'm not watching any. I'm wondering if I should watch the Dune show because. Well,
I don't know. Have you heard anything about it?
I don't know. I mean, I like the movies. I love the books, but the show, I don't know. It's like I've just seen the trailer. I think.
Yeah.
I'm not sure. Maybe some people in the chat could tell us if.
What do you think? Is anyone watching Dune? I'd be curious to know what the because it's not that I mean, I'm sure I could check it out, but it'd be kind of fun to know what people think about it. There's Dune. There's also.
At some point, I should watch your show. I still haven't watched the Stargate.
Oh, Stargate! Oh, Stargate definitely has some sciencey stuff, but mainly it's character-y stuff. So I totally understand if it's not your thing. But
I don't know. I should.
We have to check it out. Now you have to. Yeah, it's true. You're forced to. The other thing you should check out is Isaac Arthur, who does I don't know.
I watched a lot of his channel.
I love his stuff.
Yeah.
I mean,
it's really serious. I mean, it's speculative, of course, but it's he's really good and he's really thorough. So this is I like a lot.
He's like OG. He's like the original science fiction as a speculative science, which I love.
Right.
Which
is useful, which is good to do.
And any sci-fi novels? Do you read any sci-fi as well?
I used to read more than now, but
me too.
Sci-fi stuff, but
you like the Dune?
I read the first Foundation.
Oh, me too. Yeah, I only did the first one. Yeah.
Yeah, I did only the first one. I like the science fiction part, I didn't really like the characters and the style, I guess, so I didn't continue. But
The
I love
show
Dune.
is beautiful. The show is,
Okay.
if you, I mean,
I
it's
should really see that one.
it's a hard one to do as a series, frankly. Like, I'm not sure I would have chosen Foundation as the
Very long time.
yeah, but but the effects are beautiful, and it's got one of my favorite actors, Jared Harris, is in
Yeah.
it, which
Okay.
is great. So I love him. He's amazing. So Dune and the Dune books were fantastic. I absolutely loved them.
Yeah. It's amazing.
Anything else? Any other ones that stuck out for you?
Yeah, well, when I was young, I read a lot of Jules Verne and
Oh wow, that's the old style stuff. Yeah,
H.G. Wells.
Oh yeah, yeah.
The old stuff. Yeah, this was really, really good.
The classics are fun.
Yeah, the classics. Then I mean, recently I haven't read so much sci-fi. I should probably get back to.
Any recommendations for people? Did you? What about like The Martian and that kind of stuff? Like, what about the? Because that was fun because it's very science based.
Yeah, The Martian I enjoyed a lot actually.
Yeah. I like that and the movie. Frankly, I thought they were both well. I mean, other than there were some issues just to make them exciting, I guess. But if you move your head pulling,
sometimes I like things that are not so good.
Oh yeah,
scientific, like Total Recall.
Yeah. Arnie. Yeah.
I mean, Arnie is just great.
Yeah, I'm the same. I watched.
I don't like only the things that are really scientifically accurate. I'd say.
Well,
I like Star Wars.
That's Star Wars, exactly. Yeah, Star Wars. There's nothing scientific about Star Wars at all. But
it's fantasy, but it's nice.
I'm the same. There's definitely sort of. I almost think of them as fantasy. I don't even think of them as science fiction anymore. But although there's definitely some stuff that I was sort of inspired into. I mean, a lot of my interest in robotics and the sort of the cyborg side of stuff definitely came from my Star Wars days for sure. So, look, Xavier, thank you so much. I will put you must before you leave. You have to give me those links, and I'll put them in the description. Anyone else? Any questions or anything just before we go? I'm going to wrap it up because we have more than used our time with Xavier here. I'll say thank you all to everyone. Again, thank you so much for joining us. Thank you to Agne for helping out, making this possible.
Thanks to you.
Huge thanks to Cal if she's in the chat, and of course to everyone else for joining us. So. Be safe, be kind, be brilliant. Until we geek again, I'll say cheerio and huzzah. Huzzah. Thanks very much. All right.